Okay, now we can go. So, welcome everyone, good afternoon. If you're here, I hope you want to learn about how to write bad code, which is something I have a lot of experience in, as I've written a lot of it. But also I hope to bring some clarity and some ideas. So a bit about who I am. I'm a backend engineer. I have around 5 years of experience in backend. Previously, I worked in physics, doing computer simulations in C++. Python is way more fun. Right now, I'm working at Loca. We're a company that works in AI, software development, and apps, especially in the healthcare and education and other industries, I forgot. And here, I've encountered the possibility of working with many clients who want the best of the best in terms of speed. So this brings us to the point of this talk. So as mentioned before, I want to help trigger that pattern recognizing part of your brain, the same part that sees faces in arepas and in clouds, to identify async code smells, so that whenever you see a PR, whenever you see, or you are writing code, and you see this kind of pattern, you're able to recognize it, and hopefully you're able to fix it. I am not going here in this talk to talk about how the implementation of the event loop goes. I am not going to re-implement the event loop here, as other people have done it before me and better than I. I am not going to compare tools. I am not going to talk about different backends, different event loop implementations. I am also not, and I'm going to try to stay very far away from the discussion between programming techniques and parallelism and asynchrony and all of that. And I'm also not going to touch in-depth Python core concepts like the global interpreter lock and threads and everything, because as I said, other people have done it and they do it better than what I can do. So, I want to start by talking a bit about where are we now in terms of asynchrony in Python. And this is, oh, okay, here it's kind of okay. And there you go. So, in Python 3.5, we got the async await keywords, which are kind of the sugar syntax that makes all the asynchrony go around. In 2017, we got ASCII 2.0, which set the stage for true asynchrony in the backend world, which is where I come from. We got Fast API in 2018, and besides the other thing that happened in 2020, we got async support in SQL Alchemy, in Django, then Flask, and a lot of libraries have been adding support for this. And whenever you see something around the async thing, you usually get a phrase, an idea that I try to summarize with that short phrase. Basically, you should be doing asynchronous Python because it's faster. And why it's faster? Because your program doesn't stay idle, doesn't stay doing nothing, while waiting for something else to return a result. So I want to step a bit into this and take and dissect this phrase and see if this is actually the case. If we are actually writing faster code when we are doing async Python, and when are we making our code slower by not doing async properly? What's the difference? And I said that I wouldn't discuss about the programming philosophical discussions, but this is a necessary parenthesis that I need to make before actually getting into the meat and bones of the thing. And it's what is the difference between synchronous programming, asynchronous programming, and parallel programming. So let's have a very healthy dinner of frozen pizza and salad. And you want to make this, and you have 3 options. You may have more, but I'm sticking to these 3 here. So in the first option, you're doing everything one step at a time. You you open the pizza box, which is frozen, you put it in the oven, you sit staring at the oven for 10 minutes, waiting for the pizza to come out, You put the 10 minutes pass, you bring the pizza out, then you make your salad, which is quicker. You don't have to wait for that. You just chop some vegetables, put it in a plate, throw some olive oil on top, and there you go. Dinner's ready. That would be the synchronous option. You did everything one step at a time. But as you can see, and if you ever cooked in your life before, this is not the smartest move. What do you want to do? While your pizza is in the oven, you want to put a timer. And you don't want to stay staring at the oven. You want to, while the pizza is getting warm, you want to chop your vegetables and get the salad ready so that whenever the pizza comes out, is warm, is ready to eat, your salad's ready, you can sit down and eat. And you have this third option, which involves having a friend available and involves having time and logistics. So the first step is, if you have your friend available, you can call him and say, okay, you are going to make the pizza, I'm going to make the salad. This would be the parallel approach, which has other complications, which I'm not going to step a lot into, but basically the difference is that for the parallel option, if you are making the pizza, you would still be waiting. Even if the salad's getting made in another place, you would still be waiting for your pizza. So let's go out of the kitchen and come back to the programming world, and let's discuss two kinds of waiting in programming. This is not an exhaustive list by any means, but we can broadly define two kinds of waiting. Whenever you're waiting for something else, for an API to return a response, for a write to your database to happen, or you can wait for your own computation if you're running a really hard numerical problem, for example. So whenever we are talking about waiting for something else to return me a result so that I can work with it and I can process it and I can return it to my client or whatever, that's when we're talking about IO-bound waiting, let's say. And whenever we're talking about a process that it's hard to complete and that takes time because it's a lot, let's say making 1,000 salads, back to the metaphor, that's CPU-bound. So async programming is more suited for IO-bound kind of problems, because it's not because it's hard, it's because you're waiting. It's like the pizza in the oven kind of thing. You're not really doing anything, you're waiting for something to return a response. So, what do we do now? So, first parentheses that I want to do before I get into the actual code smells. I want for a thing to be very clear, and it's what a waiting is. So, how do we see this? What we need to do is we need to understand, not in depth, but at least on a very broad sense, what the event loop does and how it works. So, I went and asked ChatGPT what the event loop does. And this is what it answered. The event loop manages the execution of asynchronous operations by continually checking a queue for tasks that are ready to be executed, allowing the program to run non-blocking code while still processing events. So, let's unpack that phrase. What are async operations? Async operations are tasks, functions, methods, whatever you want to call them, that depend on something else to return. So a call to an API, it's an asynchronous operation. And what are tasks that are ready to be executed? Tasks that are ready to be executed are those tasks that either have not started waiting, so I still haven't made the call to the API or the write to the DB, or they already did and got the result back. So those are tasks ready to be executed. And non-blocking code is code that basically runs fast. So you are not waiting on anything I/O nor waiting on anything CPU bound. So having said that, let's look at some very naive implementation of an event loop. So I'm running this in a Marimo notebook, and let's hope it works. I'm going to skip over this one, as I want to focus on a realer implementation, which is using generators. I'm hoping that you have some sense of familiarity with generators in Python. the key being the yield keyword here. And this will make sense in a while. So here we have our event loop, which is the generator event loop, and it has the run almost forever method, which is the one that basically checks for tasks that are ready to be executed, which are the ones belonging in the ready list. And if they are tasks there, then it executes them until the next, like in the context of generators, until the next thing is about to come out, let's say in very broad and rough terms of what a generator does. And we have the task, let me bring it back for a moment. We have the task class, which is basically really just a wrapper that handles the execution, in this case of the generator, for the next step. So we have this implementation, which, as you can see, here I have a generator, which is almost a coroutine. So if you could imagine for a moment that instead of def, we have async def, and instead of yield, we have await, then this would be basically a coroutine, something that can be awaited, which is the core of async Python, basically, which is what we got in 3.5, a more sugar syntax way of working with coroutines and asynchrony. So let me run this and hope it doesn't break so that you can see how it actually behaves. So it starts, it does stuff, like before, waits, then it goes to the last yield and then returns. So as you can see, every time we come to the yield, there's a stop. But before that, we run all the code. So whenever we hit the yield, or in the case of coroutines, the await keyword, the event loop does that call, whatever this is in this case, oh, I forgot to, I don't know if you caught it, let me briefly show it again. I built a dummy library, let's say, which is this async spam and spam, which basically just sleep and return whatever time they were made. So if we go back to the almost a coroutine implementation, then we'll see that it basically goes through every step. And we actually get async behavior from this. So if I were to run this, you can see that this starts, and after it starts, it returns. So with asynchronous behavior, this is basically what you want. You want to start one, wait for it, and start another. So here we step into the big problem that we have with awaiting and with the await keyword, which I think is really, really badly used and is the biggest code smell. And what's the problem with this? It's the fact that it doesn't do what you might think it does. So if you have this, you can see that it goes through each task and it doesn't do it asynchronously as we just saw. It does it synchronously, basically. This is what we would expect from a synchronous thing. And await, it tells the interpreter exactly that it should wait, that it should stop. So if you are abusing await, then you most likely are writing synchronous code within your supposedly asynchronous world. So, and I want to actually show you in code how this looks, because I want you to feel the pain of seeing it not run properly. So this is real. I didn't make up those results. So let's go with the right tools. So what can you do? So what you can do is first identify, and this is the pattern part. So these are the 4 code smells that I want you to get in your brains, and whenever you see any of this, you jump and say, hey, this is bad. Put a comment in the PR, or you change your code. So the first one is really easy. Actually, the first 2. Those are quick wins. If you're defining a coroutine without awaiting anything inside, change it. It's not a coroutine, it's just a regular function. Define it with def. Maybe you're also using a blocking library whenever you're running within a coroutine. So do the homework. Find if whatever you're trying to do has async support. And if it doesn't, then do it outside of the sync paradigm. Run it synchronously. It's not a problem. Usually libraries are optimized for this. And the last 2 points are the code smells, which is something that I've seen a lot. I'm guilty of them as well, which is awaiting inside loops, which please never await inside a loop unless you really know what you're doing. And the second point is having multiple awaits one after another, as I showed previously. So let me go back to the code. So this that you have here is basically everything that is bad summed up. And I'm going to run it, and I'm going to let you feel the slowness. There you go. So we are running async because we're using awaits, we're using async def, we're like using all the fancy things, but we're still having 6 seconds in something that, as you might see, is not asynchronous. If this is this exact same thing, but done pure synchronously without the awaits, and it takes basically the same time to finish. So if you have like these 4 poor programming async techniques, then you're basically just doing it synchronously. And if you're doing synchronous within the event loop, you are like wasting the event loop. So what's the solution for this? So we have your new best friends, hopefully. We have gather, create tasks, and task groups. I'm going to go a bit into detail into how each of them works, but the core idea is that gather runs multiple coroutines, so this one actually takes a lot of coroutines and runs them asynchronously. Create tasks is great for scheduling things. Maybe you don't need these now, it's something that can run in the background, but you have to be careful because, as I say in the task group description, gather and create task have one small problem, and it's that if you don't reference things properly, they will get garbage collected and your task will disappear. And that's hard to find out. So let's see them in action. And let's go here. So basically, let me run this so that you can feel I am, in the first example, awaiting inside the loop. And in the second example, I'm using gather, which is basically takes everything and runs. So there's your difference. So gather is actually faster. Asynchronous looks like it's faster, but you have to do it properly. Let's see it with create task, and I'm going a bit faster here. This is a real example of how gather would be used, in case you're wondering, like in the real world, how it looks. But let me go over this. So this one has 2 tasks. One that I need immediately and one that can run later. So let me run this so that you can see how this works. So later it started, then I immediately did the thing, and the task, the rest of the task, ran afterwards. So create task is really good for things that you might want like not run immediately after you do it. For example, if you need to send an email to a customer that just signed in, maybe create task is what you want and what you need. But you have to be, as I said, careful, as it might break something, and if you don't reference properly, then it might break. I have here an example, which I'm going to just briefly show you, that this is a very extreme example, but I wanted something concise that would break. So as you can see here, I start 4 coroutines, but just 2 of them finished. The other 2 vanished, so careful. And last, we have task group. Task group is basically gather, but ensuring that you don't mess up your references. It's an async context manager, which is why you use it with the async with. And this basically ensures that you have what you expect. So you add the tasks. The API is the same as the create task API, but this one ensures that after the context manager exits, let's say, the task will return and you get the results with this, with the result keyword. So this is awaiting, as I mentioned, this is a code smell, which it's not asynchronous. Imagine that getting the data and getting the size are two queries that you're running. So one select and one count, for example, which is something that I usually encounter when I need to return responses in an API. I have to return the data, but I also need to return how many data there is like in total. So if you're getting this data with await, then you're not being asynchronous. But if you use task group or gather, then they get executed like asynchronously as you expect. So let's use everything and fix them. We could have two approaches. I'm going to just show the gather approach, and I'm going to show the task group approach, which I think is healthier because it helps with the avoiding the mysterious vanishing because of the garbage collection. So let's run this, and let's see if it takes as long as the other one took. And as you can see, it's not that much complicated. It's just a couple of tweaks to what we had before, if you remember. So let's run this. There you go. So we came back from 6 seconds to just 1 and a bit. So this is truly what asynchronous is supposed to be doing. This is how async is supposed to work. But you have to be careful. And let me quickly skip through this, which we already see. And it's when you don't want to go like fully asynchronous. Like, I know it sounds nice. It has happened to me that the first time that I learned about Gather, I just sent maybe 1,000 requests to an external API. And, well, thankfully they had proper limiting, so I got the 429 error back. But this will crash. Be careful with Gather. Don't get too excited. What you might want is the second collection of arrows here. You want some of the requests to happen at the same time, and when they come back, you do the other set, not everything, just throw them like crazy to the service, because you will crash it. So let's go back to the code. Of course, I built a cool service that basically just checks how many tasks it has currently. So this is the unsafe version, which is a proper coroutine, and it's being run with gather. This will send everything at the same time. And let's see. Okay, this is, for some reason, not running. Oh, yeah, it ran. It's just very fast. So as you can see, it breaks. So let's fix this. And we can use this with semaphore. I think that I mentioned, yeah, semaphore. Semaphore is really easy to use. It's basically just 2 lines more and 1 hit of the tab key. And this will make sure that you won't overwhelm services. So as you can see, oops, it's running concurrently, but not like fully. And there you go. So I also wanted to briefly mention other synchronization primitives. Semaphore is the main one. I'm not going to go in depth in this, but it's good that you know that they exist. Basically, they have the lock, which prevents different coroutines from accessing the same resource. You have event, condition, barrier. Look into them. It's really cool. Let's basically go back to the beginning. So what was the thing which we started is that a synchronous program is faster because your program doesn't stay idle while waiting for a result. So let's clarify this phrase. It's not because, it's if your program. And this if is really important because you are the one that's making the asynchrony, not just adding random awaits on your code. Not just because you're in Fast API and you have the async def endpoint and you're awaiting something inside, that's not making it magically faster. And hopefully it would, but it's not. So you make the asynchrony happen. So indeed, asynchronous programming is faster execution if you make your program to not stay idle, but you can make it. So there are a couple of easy wins, basically using async def only for coroutines, using asynchronous libraries when they exist. And if they don't exist, you can always wrap them and use libraries that do this kind of thing. And importantly, having awaits everywhere, and especially inside loops, it's a code smell. The next time you see code, maybe when you go back on Monday to your work, you will see, hopefully not, but a for loop with an await inside. Change it, please. At least leave a fix me there. Use gather, use task group. They're great, they work, they're not that complex. And lastly, be curious. This is something that is on the move. Check for libraries. New libraries are coming out, are adding asynchronous support. New features are coming in. So yeah, make your programs faster. And thanks.